The James Webb Space Telescope, JWST, is humanity's latest cosmic eye, reaching out across unimaginable distances. Light, captured at great distances, has traveled for more than 13 billion years. Light, however, tells us more than just a story. Of time, it reveals the evolution of our universe, shaped and stretched by its ongoing expansion. As we peer back at the most distant galaxies, we're virtually witnessing an ancient era, moving closer and closer to the inception of the cosmos, the Big Bang Theory. A foundational narrative of contemporary cosmology, daringly, asserts that our universe had a distinct beginning and is finite in age. Yet from its inception, this singular cosmic origin has received skepticism, and challenges to its validity persist even in mainstream cosmology for decades. The Big Bang Theory remained popular, especially after the cosmic microwave background. CMB was discovered in the 1960s. This weak background radiation, an all-encompassing hum across the universe, aligned perfectly with predictions of a hot, dense early universe. However, groundbreaking observations by the JWST in recent times have brought back old doubts and raised new questions about the legitimacy of the Big Bang. Through the astonishing clarity of the JWST, NASA's cosmic time machine, we've seen clusters of ancient galaxies far larger and more numerous than anticipated, putting our comprehension of the universe's origins into question. As the telescope peers back to the time when the first galaxies formed, it gives humanity a unique perspective, one that the Hubble Space Telescope couldn't fully access. Hubble was simply insufficient to recognize the extremely faint red-shifted light of these earliest galaxies. However, with state-of-the-art capabilities, we're gazing all the way back to the brink of time itself. As we journey into this unknown territory, we are confronted by an ancient mystery of how the first galaxies actually formed and whether the universe, as we know it, really has a single definitive beginning. The earliest universe was a hot, opaque place, so dense that light itself could not freely travel. This means that, no matter how powerful our telescopes are, we cannot observe any further back with light. However, we are not limited to light alone. New technological advancements are opening the door to the detection of gravitational waves, from colliding black holes that could be used as a new avenue to peer back into the universe's infancy, perhaps even into the very phenomenon we call the Big Bang. The roots of the Big Bang Theory and its growing skepticism stretch back to the 1920s and 30s, when astronomers first observed that galaxies further away appeared to be departing from us. Based on this discovery, coupled with Albert Einstein's theory of general relativity, the stage was set for the Big Bang model. Einstein's equations predicted that a static universe would be unsteady, necessitating either expansion or contraction. Observing this expansion suggested that galaxies must have been closer together in the distant past, implying an explosive beginning for the universe. The expansion of the universe has several profound implications. Not only do objects move farther apart, but the light emitted from them stretches, shifting to longer wavelengths as time goes on. Since wavelength corresponds to energy, shorter wavelengths being more energetic, this redshifting means the universe has been cooling as it ages. By rewinding this cosmic expansion, we reach a point where everything would have been so hot and dense that neutral atoms couldn't exist, leading to a uniform searing hot glow. This glow was confirmed in 1964 when astronomers Arno Penzias and Robert Wilson came upon the cosmic microwave background, a faint but pervasive radiation field echoing the universe's fiery origin. Yet, as the JWST pushes the boundaries of cosmic observation, scientists are identifying characteristics in the early universe that challenge the conventional Big Bang narrative. We see vast, luminous galaxies where none ought to be, clustering in ways that defy expectations. As a result, the Big Bang Theory alone doesn't explain these anomalies. What else might be at play? At the heart of the Big Bang Theory lies a singularity, a point of infinite temperature and density where the laws of physics break down. This is where space and time supposedly begin, but this concept, while powerful, has limitations. Consider attempting to describe everything that exists, compressed, into an infinitely dense point where our comprehension hits a wall. Even though many aspects of the Big Bang model have been supported by observations and laboratory experiments, this initial singularity remains an enigma, begging the question, could a different kind of beginning exist? In its journey to understand the cosmos, science has found ways to recreate similar conditions. Quark-gluon plasma, for instance, has been synthesized in laboratories. Pairs of matter and antimatter have been created to align with early predictions about the universe. Through these experiments, and by studying the cosmic microwave background's fluctuations, we have an accurate representation of the universe's evolution, but significant mysteries remain. For example, if all regions of space were once compressed into a single point, why do we observe such uniformity in the temperature of the universe? In conventional designs, spaces should display varied temperatures, since they would not have had the time to swap energy or information. Additionally, we might expect to find remnants from the hottest epochs, such as magnetic monopoles or spatial anomalies, but none are observed. These discrepancies open the door to new possibilities. Either the universe inherently possessed these balanced properties from the outset, or some mechanism imposed these circumstances. One candidate explanation is cosmic inflation, a rapid expansion theorized to have occurred before the Big Bang itself. On December 7, 1979, physicist Alan Guth proposed a revolutionary theory that before the hot Big Bang, the universe experienced an exponential expansion. This inflationary phase might be responsible for why the universe appears flat, isotropic, and homogeneous. After inflation, the universe would transition into the hot, dense state associated with the Big Bang, setting the stage for stars, planets, and galaxies to form. However, scientists now understand that cosmic inflation doesn't solve every problem. For example, groundbreaking observations by the JWST have revealed remarkably massive galaxies from the universe's infancy, suggesting an accelerated formation. Rate that inflation alone doesn't explain the JWST's incredible capabilities offer humanity an unprecedented glimpse into the cosmos. This $10 billion infrared telescope has captured breathtaking images of the early universe, revealing a variety of massive, bright galaxies that existed when the universe was only a fraction of its current age. While astronomers previously considered themselves to have a solid comprehension of how matter coalesces to form the first galaxies and stars, the latest findings suggest a much more rapid evolution than expected. These observations have stirred excitement and caution among scientists, as they are forced to revisit fundamental assumptions about galaxy formation, according to Erica Nelson, an astrophysicist. Galaxies observed within the first 500 million years of cosmic history defy existing models. The JWST is still in its infancy, but results suggest that galaxies in this early epoch may be significantly larger and more numerous than previously thought, potentially housing masses comparable to today's large galaxies like the Milky Way. The challenges that this rapid growth poses to cosmological models, which propose that a galaxy of such size wouldn't form until 1 to 2 billion years after the Big Bang, are significant. Nelson's research suggests that it's possible that galaxies are expanding more vigorously than anticipated, resulting in the possibility of new theoretical frameworks for the evolution of the galaxy. Dark matter, mysterious and invisible substance, is thought to make up about 85% of the universe's mass, shaping the large-scale structure of the cosmos. Conventional cosmology suggests that halos of immense size help galaxies form, as dark matter gravitationally draws in ordinary matter, allowing stars and galaxies to colliders that have yet to be observed. Challenges this model as galaxies appear to be forming in ways we can't imagine. Understanding the distribution of dark matter and dark energy's presence, an equally elusive force responsible for the universe's accelerated expansion, further complicates the picture. Some models suggest that early dark energy, a temporary boost in dark energy density, could have accelerated galaxy formation, potentially aligning with JWST findings. However, these adjustments need to work together with the larger context of the standard cosmological model, which has successfully explained cosmic evolution on scales as impressive as the Big Bang theory. It's not the only explanation for the beginnings of the universe. Numerous different theories have gained attention, each offering unique perspectives on a state that is barely static. In contrast to the Big Bang theory, the steady-state theory suggests a universe without a beginning, where matter appears frequently as the universe expands. This theory proposes that new matter emerges as galaxies separate, preserving a uniform density. However, it failed to account for the cosmic microwave, background CMB, which firmly backs a hot, dense early universe. The mirror universe theory proposes a more speculative idea that the Big Bang was the birthplace of two universes, one moving forward in time and the other inversely. This twin universe would evolve in reverse, serving as a mirror representation of our own cosmic past. Though highly hypothetical, it suggests that the universe may be more intricate than previously thought. The digital simulation hypothesis suggests the possibility that our universe is a simulation crafted by an advanced civilization. Quantum entanglement and the peculiar nature of space-time lends some conceptual weight to the idea, although it remains unprovable. The simulation hypothesis touches on questions of predestination and reality, redefining our perception of existence. The multiverse theory, a popular alternative, suggests an infinite number of universes, each with its own physical laws. According to this model, dark energy fluctuations trigger multiple Big Bang-like events, producing a vast multiverse. While our universe expands, creating a void of dark energy, this model implies a continuous cycle of creation, collapse, and rebirth. Each of these theories provides original perspectives on cosmic origins, posing new questions about the nature of space-time and matter. While the Big Bang theory remains the prevailing explanation, it has been challenged and reshaped by new evidence and new points of view. The James Webb Space Telescope (JWST), with its unparalleled sensitivity, is poised to unlock even more secrets of the universe, challenging long-held assumptions about the cosmos and its origins. From its inception, the JWST provides fresh perspectives on the ancient universe. It is evident that the cosmological field is at a crossroads. Discoveries made possible by this instrument might push us to rethink our entire understanding of the cosmoside's origins, its development, and destiny. In the end, the deeper we look into the universe's infancy, the more mysterious and complicated it becomes. One of the most profound implications of these findings is the realization that our current understanding of cosmic evolution may be incomplete. The emergence of unexpectedly large and mature galaxies in the first few 100 million years challenges not only the Big Bang model, but also the assumptions about how galaxies form and grow. If these galaxies were indeed capable of forming so rapidly, then the galaxy evolution-related processes may include more variables than previously thought, such as unknown interactions between dark matter and ordinary matter, or additional unknown forces in the early universe. This has resulted in the emergence of newer theories that were once considered fringe ideas, but now merit more serious consideration. One such theory is the cyclic model of the universe, which implies that the universe goes through endless cycles of creation, evolution, and destruction, with no clear beginning or end. In this model, the Big Bang is just one phase in an infinite cycle of cosmic rebirths. Each bang may give birth to a new universe, while the universe collapses and shrinks into a massive crunch at the end of each cycle, only to rebound into a new phase. This idea, while speculative, corresponds to some of the most recent discoveries in cosmology, such as conceivable changes in dark energy. Another intriguing hypothesis is the landscape multiverse theory, which posits that our universe might be one among an infinite number of universes with distinct sets of physical laws and constants. In this scenario, the formation of galaxies, stars, and planets as we observe them may simply arise as a result of the particular laws of physics in our own universe, with other universes having vastly different properties. The nature of these parallel universes could be far beyond our comprehension. Yet their existence is hinted at in the cosmic observations that challenge the standard model. This possibility has significant philosophical and metaphysical implications, raising questions about the uniqueness of our existence and the ultimate purpose of our cosmos. Beyond the practical versus theoretical difficulties in comprehending the universe's origin, the challenges are immense. While the JWST has revealed breathtaking images and data, converting this data into a coherent theory of cosmic origins will necessitate not only additional observations, but also the development of new models and tools. Increasing precision with which the universe can be observed is both a blessing and a curse. Each new discovery brings new puzzles that demand deeper understanding. The birth of the first stars, the role of dark matter in shaping galaxies, and the mysterious influence of dark energy, these phenomena are interconnected in a complex web of cosmic interactions that remains only partially understood. Moreover, as we continue to push the boundaries of our observational capabilities, we face the potential for even more groundbreaking discoveries. When we finally detect gravitational waves from the earliest moments of the universe, will we uncover other, even more distant objects, perhaps evidence of pre-Big Bang conditions? Such discoveries could help piece together the puzzle of how the universe evolved from an infinitesimally small, dense point to the vast, spanning cosmos we see today. In the end, while the Big Bang theory remains the dominant paradigm, it is clear that our comprehension of the universe's origins is far from complete. Cosmic inflation, the multiverse, cyclic universes, and even the possibility of higher dimensional space could offer new frameworks for interpreting the data. As our technological and data-gathering capabilities continue to evolve and our models improve, one thing is certain: the quest to understand the origin and evolution of the universe is far from over. What the JWST has already shown us is that the universe is far more complex and fascinating than we could have envisioned. From galaxies formed in the universe's infancy to the mysterious forces shaping the cosmos today, each observation offers deeper knowledge of the universe's past, forcing us to challenge long-held assumptions and reevaluate our understanding of existence's very nature. The questions that remain are daunting but also exciting. The future of cosmology, with the JWST at the forefront, promises to reveal even more astonishing secrets concerning the universe's past, present, and ultimately, its future. As we venture further into the unknown, we are not only learning more about the universe that surrounds us, but also gaining a deeper understanding of our place in it. The story of the cosmos is still being written, and humanity is just beginning to read the first few chapters.